Hello, so in this video we are going to start talking through the normal distribution. So before we start, let's just remind ourselves of where we've come from. So far we've talked about discrete random variables and the probability distributions that can be used to describe these discrete random variables. So just remember, a discrete random variable is obviously a value that is randomly generated, okay, and it can change, so it's variable, but it can only result in a specific set of values within a given interval, okay? So usually it's integer values, for example, number of people or number of sweets in a jar, okay? But they can also be like, for example, shoe sizes, where you can have like 2 and 2.5 and 3.5 and 4.5. So effectively, a discrete random variable is a random variable that can only result in integer or specific values within a given range, okay? Now, the three distributions that we've looked at up until now that all work with discrete random variables are the uniform distribution. So just remember, the uniform distribution is if you have a situation where all outcomes are equally likely. And the example we gave to do that was the dice. Okay, we rolled a fair dice and basically the outcome of each side, so 1, 2, 3, 4, 5 or 6, they were all equally likely. And the way in which we write that is using x, so our random variable, is distributed in uniform using the two parameters a and b, where a is the lowest value that it can take and b is the highest value that it can take. Okay, so just be aware that uniform distribution, we've looked at it from a discrete context, so for discrete random variables. There is also a uniform distribution for continuous random variables as well, but we don't look at that in this course. Okay, so just be aware of that. Now, the other two distributions we've looked at are the binomial distribution, and if you remember, the way that we kind of visualized the binomial distribution was by taking a beanbag and kind of tossing it up in the air and seeing whether it landed on a bit of paper or not, okay? So basically a binomial distribution is a discrete random variable with a fixed number of trials, and each of those trials either results in a success or a failure, hence the binomial bit, the 2-but, okay? So the other distribution we looked at was the Poisson distribution as well. And the Poisson distribution was basically when an outcome occurred at a constant rate, okay? So basically if something occurs at a constant rate, for example, we looked at heartbeats within a given time interval, so per 10 seconds, per 30 seconds, per minute, per hour, then this is a Poisson distribution. It's something that occurs at a constant rate. Now, these are all discrete distributions, and these are all the discrete distributions that we will look at in this course. But then it makes sense, if we looked at distributions for discrete random variables, we should also look at distributions for continuous random variables as well. And that's where we're going to start today. So we're actually going to start by looking at this thing. So this thing which I've got on the screen here is something called a Galton Board, okay? And the idea is, if I just flick this over, you can see that there's lots of little tiny ball bearings. And you might just be able to see that they basically drop out of this little funnel here. And they drop, and they basically have to pass through a series of pegs. So you might just be able to see it if I orientate the light like so. You might just be able to see lots of little pegs which they have to make a decision. So as they drop, they basically have to decide which peg they're going to go down. You can almost imagine every single time a ball reaches a peg, they can either go left or they can go right, okay? And then basically down the bottom there's lots of little bins, okay? So when I flip this over, obviously they'll drop out, they'll drop down all of these little pegs, then they'll drop into one of these bins along the left, along the bottom here. So if I just show you, if I flip this over, you can basically see that all of the ball bearings have dropped down, they choose which side they want to go, whether left or right at each peg, and they drop into one of the bins. Now what's really cool about this is you kind of get this shape here, okay? So the majority of the ball bearings land in the middle bins. And that kind of makes sense, right? Because if they're dropping from up here, if they're dropping from the funnel up here, they'll drop down, drop down, drop down. Well, there's more routes to get into the middle bins here. Whereas there may only be one or two routes to get into the outer bins, so over here and here. Now because there's loads and loads of ball bearings in there, of course probability takes that even though there's fewer routes to get into the outer two bins, or the outer bins, there's still a chance of getting there, okay? So one or two ball bearings are always going to take the most extreme route. But as a general rule of thumb, the majority of the ball bearings end up in the middle bins, and then there's fewer ball bearings each side. So if I just show you that again, so I'll drop all the ball bearings back into their little funnel, and I'll just flip it over, Watch they drop, they're all making decisions on each of the pegs, and they'll drop into one of the bins. And the majority of the bins are down here, and then the fewer ball bearings are in the outer bins, okay? Now this makes sense. Now what I can do is I can actually skew this distribution, okay? The distribution according to which bin the ball bearings fall in. And the reason why I can skew it is because if I tip it over on its side, I'm basically putting a bias on which direction the ball bearings are going to drop every single time they reach a peg. So in this case, they're more likely to drop to the right than they are to the left. So watch this, when I flick it over, ball bearings are more likely to flip on the right, okay? So you can see that in yellow, I've got sort of the shape of the bins where, if it was just symmetric, so in other words, the ball bearings were just going to drop straight down, I wasn't biasing at all, there was an equal choice of going left or right, okay? But now what I did was when I tipped it upside down, when I tipped it like that, I'm basically saying you're more likely to tip to the right than you are to the left, so therefore I get exactly the same shape of distribution, I still get this curved shape, and the majority of the ball bearings are kind of in here. But because I biased it, it's just that the majority of ball bearings have kind of been shifted over to the right. They're more likely to land on the right side of the bins than they are on the left. And likewise, if I tip it over to the left, like so, and again tip that over, again I get exactly the same kind of shape, it's just it's now been tipped to the left rather than the right. So if you like, it's been skewed, okay? Because there's a more chance of dropping to the left than there is to the right. Alright, fantastic. So I actually want to explore this idea a little bit further and look at the mathematics behind what is going on with this thing. So effectively what we've got is a set of ball bearings, they drop down and they make a choice every single time they reach a peg. Either they go to the left or they go to the right, and we can also bias that choice either by tipping the Galton board to the left or to the right to give them more chance of going to the left than to the right, okay? So I'm going to first of all look at the case in which there is an equal chance of going left and right. In other words, it's sitting perfectly flat on my table and they've effectively got an equal chance of going either left or right, okay, much like there is on the screen at the moment, okay? So let's look at the mathematics. Now, if we want to model this situation, what we're going to do is make it simpler, understand the mathematics with the simplest case, and then we build it up from there, okay? So what we're going to do is think about it like this. Imagine a ball is just going to drop and we're just going to do it as one ball dropping, and we're going to look at the number of paths that there are of getting to each bin. Now I guess for convenience, what we're going to do is treat this as rows, okay? So we basically have, we basically have a row along the top, then we drop to the next row and then there's 2 pins, the next row there's 3 pins, next row there's 4 pins, next row there's 5 pins, etc., okay? And basically we're going to number the bins from 0 to whatever row we're up to, okay? So in this case we've got 6 rows, so therefore there are, well, 7 bins in total, but we can number them from 0 to 6, okay? Now we're going to look at the case where there's an equal chance of going left as there is right. So let's have a look at this then. Let's simplify it by looking down, first of all, the most basic case. Imagine there are no pegs. Imagine we're just dropping a ball and there's only one bin that it can land in, okay? Bin 0, okay? So there's no choices that it's making. Well, are you happy that I can model this as a binomial situation? The reason being is because every single time the ball bearing reaches a peg, it has to make a choice. It either goes left or it goes right. So therefore, if I call that as a success or a failure, let's say that my random variable, let's give it a name, x, is the number of right turns, then I can basically say if it goes right, it's a success. If it goes left, it's a failure, okay? So in this case, it's not making any choices, so therefore the number of trials, the number of choices it's making is 0. And because there's an equal chance of going left and right, that means the probability of turning right, the probability of a success, is 0.5. Okay, cool, fantastic. So therefore I can simplify this and say, well look, the probability that my number of right terms is 0, in other words it ends up in bin 0, that is equal to 1. Okay, so there we go. So the probability of the ball landing in this bin has got to be 1 because there's no choice it's making and there's a half a chance of turning left and right. Well, if it's not reaching any pegs, then there's no probability of turning left and right because it's not actually making a choice. Therefore, the probability that it's going to end up in bin 0 is certainty, is 1. So you can see over here on the right hand side, what I'm going to do is I'm going to say, well, okay, look at the simplest case. The probability of a ball ending here is going to be 1. Okay, so basically there's only one route that you can take to get to this particular peg. It literally just drops out of that funnel and lands at that particular peg. So I'm going to keep track of the number of routes to each position. Okay, so effectively what I'm going to do is keep building up the number of pegs. So at the moment I'm starting with 0 pegs. I'm going to first of all consider what the binomial distribution would look like in order to land in the relevant place. And I'm also going to look at the probability that it's going to land in each bin, okay, where x is the number of right turns. And over here on the right hand side, I'm also going to keep track of the number of different possible routes to each position, okay. So let's do it now with actually just one peg. Okay, so if you have one peg, are you happy that there's 2 bins that it can land in? So let's call it bin 0 and bin 1. Now it's making one choice. So the number of trials is going to be 1, okay? And we still have the probability of turning right, the probability of success is 0.5. But now we need to consider, well, okay, what's the probability that it's going to end up in bin 0 and what's the probability it's going to end up in bin 1? Well, the probability that it's made no right turns, in other words, it ends up in bin 0, is equal to 1/2. And the probability that it makes 1 right turn, in other words, it ends up in bin 1, that's got to be equal to 1/2 as well, okay? Because there's a 1/2 chance of it going left, 1/2 chance of it going right, which means there's a 1/2 chance of landing in each bin. Now have a think, how many different paths are there to get into each bin? Well, are you happy that there's one path to get into each bin? Either it drops and it goes left, that's one path, or it drops and it goes right, that's another path. So I'm keeping track of the number of paths over here on the right-hand side. Cool, fantastic. So let's keep going then. Now let's do it with 2 choices. So in other words, it drops, it makes a choice, it either goes left or right, then it drops into another row, and whatever pin it's at, it then has a choice, it either goes left or right. So in other words, there's 2 choices it has to make. Each ball is going to reach 2 pins, okay, and make 2 choices. So if we add another row to this, let's have a think, okay? There's now 3 bins it can end up in, bin 0, bin 1, or bin 2. Okay, so there's 2 choices it's making because it drops and then it drops again, so it's making 2 choices, and in each case it either goes left or right. All right, so let's have a think. How many different paths are there to get into bin 0, this far left bin? Well, there's only one path. It goes left and then it goes left again. Okay, so there's only one path that it makes to get into bin 0. So the probability of making no right turns would mean that you'd be ending up in bin 0, okay? So bin 0 means you make no right turns, they've all got to be left, because you go that way, and then that way, okay? So you're going left and then you're going left again, okay? You don't make any right turns, means that you'll end up in bin 0. Okay, so what's the probability of ending up in that bin? Well, look, if you go left, there's a 1/2 chance of going left, and then you go left again, so there's another 1/2 chance of doing that. So it's a 1/2 and then another 1/2. So it's a 1/2 times a 1/2, which is 1/4, okay? Now, similarly, if I just jump ahead to bin 2 here, are you happy that bin 2 is a similar situation to bin 0, except that bin 2 is they're all right turns. It's just right and then right again. In other words, there's no left turns mixed in there. So it makes 2 choices, and if both of those are right, you're going to end up in bin 2. Now, just in a similar kind of way as you were finding the probability for bin 0, you had to go 1/2, that's 1/2 chance of going right, then another 1/2 because there's a 1/2 chance of going right again. So it's a 1/2 times a 1/2, which is a 1/4. Okay, cool, fantastic. So now let's have a look at the number of ways of getting into bin 1. Well, are you happy you can either go left and then right, or you can go right and then left? Okay, so there's 2 paths which you can make in order to go to bin 1, okay, because you're making 2 choices, and one of those choices has got to be a right turn and the other choice has got to be a left turn. Well, we're defining our random variable as the number of right turns that we're making. So to get to bin 1, what we're basically saying is, what's the probability of making 1 right turn? Okay, what's the probability that x equals 1? Well, in that case, there's 2 ways of making 1 right turn, okay? So you go 1/2 and then 1/2 again, that's the probability. So you go left, which is the probability of a 1/2, go right, which is the probability of a 1/2, so that's a probability of a 1/4 that you make a left and a right. But then you could also do it the other way. You could either go right, which is the probability of a 1/2, and then left, which is the probability of a 1/2. So there's another 1/4 way of getting into that bin. So in total, there's a 1/4 chance way of going left and then right, and there's a 1/4 chance way of going right and then left, which means there's a 2/4 chance of getting into this bin here. So there's 2 possible routes, so I'm going to update the number of different possible routes in this position over here. So there's 1 way of getting into bin 0, both lefts, 1 way of getting into bin 2, both rights, and 2 ways of getting into bin 1. You go left and then right, or right and then left, okay? And these are the probabilities of getting into each bin over here. So now if I update it with another set of rows, so another 3 pegs along the bottom, each ball bearing now is going to have to make 3 possible choices, okay? So let's have a look. Are you happy that to get into bin 0, there's only one way that I'm going to land in bin 0? It's all lefts, okay? So no rights whatsoever. So the probability that I'm going to end up in bin 0 means that I'm going to make no right turns, so that's going to be an eighth. Are you happy? Because it's going to be a half, then another half, then another half chance. So that's an eighth in total to get 1/8 probability of getting in that bin, okay? If I look at bin 3, so the other extreme, that's going to be all right turns. So a half followed by a half followed by a half. That's another eighth term. So the probability that all those choices are going to be right turns is going to be 1/8 as well. Then if I have a look at the middle two bins, we'll have a look. To get into bin 1, that's going to involve at least one right turn. You can actually sit there and figure it out. So one right turn and two left. So I need to go left, left, and then right, or left, right, then left, or right, left, and then left. So basically I need to make one right turn in order to get into bin 1, and the others have got to be left. So the probability of getting up in there, well, because there's 3 routes, okay, and each route has the probability of 1/8, it's a half times a half times a half, then the probability of making one right turn is going to be 3/8, okay? Similar kind of story for bin 2, except this case, I'm going to have to make 2 right turns, okay? And a similar kind of thing, there's 3 ways of getting into bin 2, so that's a probability of 3/8. So if I update it over here, I have 1 different possible route to get into the bin 0, they're all lefts. 3 possible ways of getting into bin 1, that's basically with 1 right and the others are lefts, okay? 3 possible ways of getting into bin 2, so that's 2 rights and 1 left, and 1 possible way of getting into bin 3, that's all of them are rights, okay? And in fact, I can continue this pattern down. So if I look now at 4 choices, hopefully you notice that the number on the bottom is effectively just a half times a half times a half times a half. Just basically you're multiplying by a half for however many choices you're making, because there's an equal chance of going left or right, okay, in this case. And then the number on the numerator corresponds to the number of different possible ways of getting into that bin. And you notice that there's always a symmetry going, because in this case we're looking at the number of right turns. But because there's an equal chance of going left and right, the reason why there's a symmetry is because it doesn't matter whether I look at the number of right turns or the number of left turns. It should still be the same probabilities, okay? It'd just be backwards, all right? And you also notice that the way which I've numbered my bins, so bin 0, bin 1, bin 2, bin 3, bin 4, it corresponds to the number of pegs, the number of choices I'm going to have to make. So the number of rows, in other words, okay? And you also notice that the number of the bin corresponds to the number of right turns that I'm making. So in order to get into bin 0, I'm making no right turns, they're all lefts. But in order to get to bin 4, all 4 of those choices have got to be right turns. To get to bin 3, 3 of those choices have got to be right turns, and the remaining 1 choice has got to be a left turn. To get to bin 2, that means 2 choices are right and then 2 choices are left. And to get to bin 1, that means that 1 choice is right and the other 3 are left. Okay, so hopefully you notice a pattern. Now have a look over here at the right hand side, because I'm keeping track of the number of different possible routes there are to each position. I'm kind of doing it by counting, okay? But you might recognize the numbers if I keep going. So 1, 5, 10, 10, 5, 1. Basically what I'm doing is I'm adding together the number of routes to get to the previous positions, okay? So if you look, to get to this position here, which is going to be bin 2, so bin 2 and this position here, what I'm basically saying is I'm taking the number of routes to get to this position and the number of routes to get to this position and adding them together, okay? The reason why I have to add them together is because the only way of getting to this case bin 2 is by thinking about the number of ways to get to this peg and the number of ways of getting to this peg, and I have to combine them together because I'd have to be at either this peg or this peg in order to get to this position. Does that make sense? So basically I'm looking at the 2 diagonals each side. Then I have to add the numbers to get to those number of different routes to get to those positions together in order to work out the number of ways to get to that bin, okay? So therefore I predict that the bottom bin is going to read 1, then 6, then 15, because notice 5 plus 10 is 15. 20 there because 10 plus 10 is 20. That's got to be 15 because that's 10 plus 5. That's got to be 6 because 5 plus 1. And that's got to be 1 because there's only 1 possible route in order to get to that bin, and it's just all rights, okay? And you notice that these numbers, the number of different ways to get to each position, are the numerator of my fractions, okay? So the probability of making no right turns is 1 because that number there is 1. The probability of making 1 right turn is 5 because that number there is 5. There's 5 different possible routes to get to that position. Number that goes there is 10 because there's 10 different possible routes to get to bin 2. Number there is 10 because there's 10 different possible routes to getting to bin 3. Number there is 5 because there's 5 different possible routes to getting to bin 4. Number there is 1 because there's 1 different possible route to get to bin 5, okay? So in other words, I can work out what the numerator is really easily, and we've established that the denominator is just going to be 2 to the power of whatever choice you're making. Because effectively, every single time you get to a peg, you're having a half chance of making either a left or right turn. So basically you're doing a half times a half times a half times a half for however many choices you're making. Okay, so therefore I can predict really easily what each probability is for the sixth row, if you like, so the probability of ending up in each bin, just by thinking about the number of different possible routes to each position. By the way, this is just a combination. Okay, this is a combination. I'm thinking about the number of right choices from the number of choices that I'm making. Okay, so X is the number of right turns. How many of those turns are right? Well, I'm looking at each of those probabilities down here. Looking at each of these probabilities down here, and I'm thinking about how many different ways there are of making that many choices from 6 possible choices in total. Okay, so the reason why that is 6 is because I'm basically saying how many different ways are there of making one right turn from 6 possible choices. Answer, 6. And the reason why that number there is 15 is because I'm asking, well, how many different ways are there of choosing 2 right turns from 6 possible choices in total? Okay. Now, if you're familiar with Pascal's triangle, that's literally what's going on over here. So what's really nice is that we're actually linking together Pascal's triangle with our combination works, which we were doing before, like permutations and combinations. Okay. Hopefully you see the reason why there is that combination in the front of the binomial formula, and the reason why Pascal's triangle is so intrinsically related to the binomial formula. It's literally saying, well, how many different ways are there of getting to each of these positions? Okay. And the answer is, well, you have to think about how many different choices you've made in total, and how many of different ways are there of making that many right turns for that many choices. Okay. So if I ask then this question here, what is the expectation? So what is the expectation? What is the expected position? What is the expected bin you're going to end up in if you're making that many choices? And I can also think about the variance as well. So how much variance should I expect? Well, have a look at the probability distribution down here. So I'm looking at 6 possible choices, okay? Every single time you drop a row, I'm making 6 possible choices of either left or right, okay? And I've got the number of right turns along the top here. So this is 0 right turns, 1 right turn, 2 right turns, etc. And the probability of getting up in that position there, okay? And we've just established where that comes from. We've just looked at that, okay? So if I asked you, what is the expectation? What position do you expect to end up in, okay? Well, hopefully in this case, because I've kind of drawn the ball bearings in, remember this is exactly the same situation which is happening here. Okay, I'm basically saying, well, look, I'm making this many choices, so I'm dropping all these ball bearings down. They're each making a choice, and then what's the expected bin that it should end up in? So if you just looked at one ball bearing, which bin would you expect that ball bearing to end up in? Okay. In this case, it should be fairly obviously bin 3, because there are more routes. There's the most number of routes to get to bin 3 relative to all of the other bins. Okay, so to get to bin 3, there is 20 different possible routes to get to that bin, whereas the other bins, so bin 2 and bin 4, only have 15 different possible routes. Bin 1 and bin 5 only have 6 possible routes, and bin 0 and bin 6 only have 1 possible route. Okay, so therefore the expected bins should be 3. Okay, so that's it logically. But what if we actually wanted to work this out categorically? Well, just remember the expectation of a discrete random variable. Remember, this is discrete because you can only end up in a set bin. You can only end up at bin 0, bin 1, bin 2, bin 3, bin 4, bin 5, or bin 6 in this case. So therefore, it's discrete, and that should just basically be worked out by adding together the number of right turns times by the probability of ending up in that bin. Okay, so I just take the outcome, which is 0, 1, 2, 3, 4, 5, or 6, and multiply it by its associated probability, add it all together, and lo and behold, it comes out as 3, or about 3 anyway. Okay, so what that basically means, because if you calculate the expectation of this probability distribution, which corresponds to what's the probability of ending up in each bin, you should expect to end up in bin 3. And that makes sense, because that's got the most number of balls in and the most number of paths to get to that position. What about the variance then? Well, have a look. If I calculate the variance, just remember I use the formula for variance, use the probability distribution, and it comes out as 1. What that basically means is that the variance, and by default the standard deviation is also 1 because the square root of the variance is standard deviation, that means that the expected deviation is 1 bin away from bin 3. So I expect most of my ball bearings to end up in bin 3, but I'm not naive. I don't expect all of my ball bearings to end up in bin 3 because of the way which probability works. Like, there is still routes to get to other bins, so I do still expect ball bearings to end up in other bins. It's just the one that I expect in, the most likely bin for a ball bearing to end up in, is bin 3. So therefore, what's the variance? What's the expected deviation? How many bins do I expect the ball to deviate? It should be 1 bin each side. And that kind of makes sense. So the majority of balls should end up in the middle bin, and then you kind of end up with 1 standard deviation each side. So it basically is a decreasing probability each side, okay? Now, are you happy that this is kind of a discrete case? This is still a binomial case because it's only can end up in discrete bins, but it's still a sort of a nice kind of shape. And this is kind of illustrating why the binomial distribution kind of looks like this kind of thing which we've seen before, where there's the most likely bar in the middle with the tallest probability, and then basically it drops off each side because there's a lesser probability of ending up in each bin each side, okay? Now, the question is, how can we make this continuous? Well, the answer is very simple. We basically say, well, if it's a discrete case, is it can only end up in set bins, just remove those bins and then you've got a continuous case. In other words, it doesn't end up, the ball bearing doesn't end up in discrete positions, discrete bins. Instead, it ends up anywhere it likes. Anywhere it likes. So we remove all of the bin dividers, okay? But we should still expect this same kind of shape. So this is the shape for the discrete case, and this is now the shape for the continuous case, where the ball bearings can end up on top of each other, okay? And we've seen this before. This feels very familiar because we've seen that both the binomial and the Poisson distribution both tend to a continuous random variables. They both can tend to this kind of shape as the number of trials increase. In this case, what you're basically doing is either considering more and more bin dividers, in which case you don't really care about the bin dividers, okay? So if you can consider more and more bins, you're no longer caring about the bin dividers, in which case you're basically saying the ball can pretty much end anywhere it likes. We don't really care about the dividers. And we kind of get this shape of the distribution. So the most likely outcome is in the middle, and then you basically have smaller outcomes or less likely outcomes happening each side, okay? So in general then, as you increase the number of trials, you basically get a discrete case tending towards a continuous case. And this is kind of our entry into the normal distribution. It's basically using what we've already seen before with both the binomial and the Poisson distribution. It feels very familiar. And we're just basically saying, well, okay, if we want to turn this discrete distribution into a continuous distribution, just simply consider what happens as you increase the number of trials, okay? Because of course, if you increase the number of trials, what you're basically saying is that actually I don't no longer care about the bin dividers, because those bin dividers are going to basically be irrelevant. So I kind of like you're zooming out on this thing. If you zoom out on this thing, you're no longer able to see the bin dividers. Like if I hold this thing back here, you're probably not going to be able to see those bin dividers anymore. You just see the overall shape of the distribution. That's literally what's happening here. So we've considered what happens in the discrete case with the binomial distribution. We've understood the probabilities, the number of different paths to get to each bin. But then we basically say, well, okay, let's just add loads and loads of bins there. Well, in that case, the bins kind of are irrelevant anymore. We get a discrete distribution tending to a continuous distribution instead. So that's the binomial and Poisson probability mass function. That's the shape, which we've explored before. So basically what I'm saying now is if you basically zoom out, the gaps between each of these different bars, so you can see all of these different bars, the bins if you like, the gaps between them will become irrelevant. Therefore, the discrete distribution will tend to continuous distribution. It'll just look like a small curve. And we've just seen that the most likely outcome, the mean, is in the middle, and then you're basically looking 1 standard deviation each side of the mean. Okay, and that's basically how you understand how those probabilities are distributed. Okay, so we call this the normal distribution. Why is it called the normal distribution then? Okay, well, normal distribution is dealing with a continuous case. Okay, so binomial, Poisson, they're both discrete, so therefore we call it the probability mass function, or a PMF for short. If we're looking at the continuous case, it's still a probability distribution, but we call it instead the probability density function. It's kind of the difference between mass and density, I guess. But density is basically saying, well, look, you no longer care about the gaps. There's no gaps. It's all continuous, okay? So therefore, you're dealing with a density function, whereas if you have gaps, you can only have set discrete values. Therefore, we call it the probability mass function. So it's just to be important aware of the difference between a PMF, probability mass function, it's discrete, and a PDF, probability density function, it's continuous, okay? So what are the two parameters we're interested in with the normal distribution? Well, fairly obviously, we're interested in the expectation. We're interested in the average value of our distribution. Okay, so that's mu. But we're also interested in understanding what the distribution is, because we don't expect all of our ball bearings to end up in this middle bin. We expect there to be some kind of natural deviation each side. And the natural deviation is determined by the standard deviation. okay? So basically the two parameters of a normal distribution for this course is the mean and the standard deviation squared. We tend to give it in terms of the variance rather than standard deviation, but it's a similar kind of idea, okay? Now, are you happy? We've already discussed this. The most likely outcomes are the outcomes which occur most closely to the true average, to the mean, okay? And then outcomes further away from this have a rapidly decreasing probability. And we basically say that most of these outcomes should occur within 3 standard deviations of the mean, or at least 3.5 at an absolute push. But we basically say that within 3 standard deviations of the mean, these are the most likely values, because we expect there to be some natural deviation. We don't expect all the ball bearings to end up in this middle bin. We expect there to be a little bit of deviation each side. And we basically say that the expected deviation is about one standard deviation. And if we look about 3 measures of standard deviation, 3 units of standard deviation, each side of that mean value, we should have the majority of our data. Anything outside of that, we'll consider that an outlier. Because of course, if I was going to just sort of take away all the bins and allow the ball to land anywhere, there is a chance that the ball could land way out over here. But it's a really reduced chance, so we would call that an outlier. We'd call that a really unusual case, okay? Now, this is the probability density function of a normal distribution, and it's horrible. This is basically the probability of an outcome occurring. So if I asked you, what is the probability of it ending up in this particular position here, you'd have to use this formula, okay? And it's not a nice formula to use. It's possible, but it's not a nice formula to use. So what we tend to do instead, if it's a continuous case, we're usually interested in looking at less than or greater than cases, or values between a particular value, okay? So with discrete values, we are actually interested in what is the probability of getting those discrete values. In other words, what's the probability that our outcome is equal to some particular value? That's less important with a continuous case. I mean, if you think about it, if you take a continuous random variable, such as, for example, time, I mean, that could be a decent continuous random variable. If you look at time as a continuous random variable, it's unlikely that we're ever going to look at the case, well, what's the probability that you're going to be exactly equal to this particular value? What you're more likely to ask is, what's the probability that you're less than this particular value? Or what's the probability that you appear greater than this particular value? Or what's the probability that you appear between these two particular values? So instead, what we look at is a cumulative distribution, okay? Now, it's really important. The reason why we call it the normal distribution is because most things in life follow this normal distribution. They have kind of most values occurring in here and then fewer values occurring further away from the likely value, further away from the mean. So if you look at like heights of people or durations of pregnancy or marks in exam, most things in life follow this distribution. Hence we say it's normal. It's normal for things in life to follow this particular distribution. Particularly if you look at heights of people, like you expect most people to be around the 5 or 6 foot mark. About the 6 foot mark, right? So you expect most people to fall in here. But if you've got a few really small people and you've got a few really tall people, so this is the reason why it follows this particular curve, okay? Now, this is an awkward function, like I say. So what we're most likely to look at is either less than, greater than, or between, okay? Now just be aware that because we're dealing with a continuous random variable now, okay, and we're no longer interested in looking at exactly one particular value, we don't actually care whether it's less than or equal to. These would be considered exactly the same, okay? And the reason being is because it's continuous, and if you've ever seen the proof for y 0.9 recurring, so in other words 0.999999999, it's exactly equal to 1. So actually, we're no longer interested in that infinitesimals. When we're looking at discrete random variables, less than and less than or equal to are very different. For example, what's the probability that x is less than 3? Well, that will basically be the probability that x is equal to 0 plus the probability that x equals 1 plus probability that x equals 2 plus the probability that x equals 3. But if I'm looking for the probability that x is less than 3 with a discrete random variable, I'm basically looking at just probability that x equals 0, probability that x equals 1, and probability that x equals 2, not that probability that x equals 3 as well. We don't care about that with continuous random variables. So actually in this case, the probability that x is less than some particular value will be exactly the same as the probability that x is less than or equal to some particular value. And the same for the greater than or the betweens as well. So don't worry about the difference. So don't worry about the fact that it's less than or equal. Because we basically say that that thing will be exactly the same as this thing here. So it'll be exactly the same, that probability that x is less than or equal to some particular value. Because it's continuous, we don't care. If it's discrete, obviously we do care, we still care about that. But because it's continuous, we can take any value, we treat these two things exactly the same. So don't get too hung up on that. Now, here's the idea, okay? So we've basically said that most of our values will occur between 3 standard deviations below the mean and 3 standard deviations above the mean. And because we're looking at cumulative probabilities, the area underneath that graph is basically what happens if we add lots of infinitesimal equal to's together. So what's the probability that x is equal to negative 3 standard deviations? What's the probability that x is equal to less than negative 3.5 standard deviations? Okay, we're looking at lots of individual equal to probabilities together, and then we can look at intervals. So in this case, what we're actually interested in, a continuous random variable, is no longer the height of the curve, but actually the area underneath the curve. Because of course, if I take a curve that's looking like this, so this is my probability mass function, okay, for my particular outcome, then basically what I'm going to do is say, well, okay, I'm only interested in outcomes that are less than some particular value. So let's say I'm only interested in values that are less than that particular value. Well, of course, the height of that curve will be the probability that x is equal to some particular value. So this will be x is equal to some particular value. This is also x equal to some particular value. So what I'm basically doing here is adding together lots of probability that x is equal to some particular values together. And you can see that if I add lots of infinitesimal values together, you can see that what I'm basically getting is an area. Okay, so this area underneath the curve will correspond to the probability. And this is all to do with integration. We'll meet this again when we look at integration. But what that means is that we need to understand, if we're not going to use this horrible probability density function, this thing up here, what we need to do then is understand, well, okay, what is the probability that x is equal to certain particular values? So for example, we basically know this, and I'm just going to give it to you. We know that any value, any probability that is less than 3 standard deviations below the mean, so this particular region down here, is 0.15%. There's 0.15% of your data that is expected to end in this value here, okay, in this region here. If you're thinking about it from your Galton curve, there's basically about a 0.15% chance of a ball ending up over here, okay? Now, if we look at the next region, in other words, between 3 and 2 standard deviations below the mean, there's about a 2.35% chance of your data ending up in here, okay? So 2.35% chance of your data ending up between 3 and 2 standard deviations below the mean. If you look at the probability of your data ending up between 2 and 1 standard deviation below the mean, there's about a 13.5% chance ending up in there. And if I look between 1 standard deviation and the mean, I'm expecting about 34% of my data to fall in that particular region. So in other words, 34% of my data should lie sort of that side of the mean, between 1 standard deviation and the mean itself, okay? Now, because this curve is symmetric, I've basically looked at it from the case that what's the probability that you make a left or a right turn? They're equal, okay? So the half chance of making a left turn, half chance of making a right turn, okay? Which then basically means that these probabilities will just be repeated over here. So you see the probability of ending up 1 standard deviation below the mean is exactly the same as ending up 1 standard deviation above the mean, okay? And the probability of ending up between 1 and 2 standard deviations above the mean is exactly the same as the probability of ending up between 1 and 2 standard deviations below the mean, and so on, and so on. Okay? So in other words, we end up with a curve that looks like this. If you're looking at regions where you're looking at integer numbers of standard deviations above or below the mean, you can just use this curve. Okay? So let's actually have a go at some of these questions then. So let's have a go at question 1. So we've basically been given that x is a normal random variable, so it's distributed normally. The mean is 4, the mean is 4, and the variance is 9, so 3 squared. So remember, the number that always goes there is always the variance, okay? So let's suppose we want to find the probability that x is less than 1. So what we're first of all going to do is draw ourselves a probability curve, so our normal distribution curve. So I'm literally just going to draw it in like this, okay? And I'm actually going to refer to this thing on the screen, okay? So I'm actually going to refer to this probability function here, this probability density function here, okay? So what's the most likely value? So what's the value that goes in the middle? Well, in this case, it's the mean, it's 4, okay? And then I basically know that I'm looking at 3 units of standard deviation each side of the mean. So let's draw that in. So I'm going to put 3 standard deviations each side of the mean, like so. That's what each of those bar represents. And what is the unit of standard deviation? Well, are you happy the variance is 3 squared? That's given in my normal distribution formula. So therefore, my standard deviation has got to be 3. So if I'm looking at my standard deviation unit as being 3, that basically means that 1 standard deviation unit above the mean is going to be 4 plus 3, because my standard deviation unit is 3, okay? So the number that goes there is going to be 7, because that's 4 plus 3. And the next one is going to be another unit standard deviation above the mean. So that's going to be 10. And another unit standard deviation, that's 13. And I can do exactly the same in the negative direction as well. So it's going to be 1, that's negative 2, and that there's going to be negative 5. All right, fantastic. So now if I want to find what is the probability of my random variable having a value of less than 1, well, basically what I'm going to be looking at is what's the probability that I'm going to end up in this particular region here, okay? So if I look for that probability, then I can basically just refer back to this particular curve here, because I know that these areas should correspond to these particular proportions on the screen. So basically I know that the probability of ending up between or less than 3 standard deviations below the mean is 0.15%. So I know that that probability between negative 5 and below is 0.15%, okay? The probability of ending up between 2 and 3 standard deviations below the mean is 2.35%. Again, I'm just using my curve here. And the probability of ending up between 1 and 2 standard deviations below the mean is 13.5%. So in other words, between 1 and negative 2 is 13.5%, okay? So all I need to do to work out the probability that x is less than 1 is add these 3 regions together. So in other words, it's going to be 0.15% plus 2.35% plus 13.5%. So if I add these 3 regions together, that's going to be the probability that x is less than 1. So that's going to give me 16%, okay? So that's going to be 16% that my random variable for this particular distribution, so with a mean of 4 and a variance of 3 squared, the probability that I choose a value which is less than 1 is 16%. Or another way of interpreting that, 16% of my values should be less than 1, okay? So both ways are fine. If I have a look at this probability, so if I want the probability that x has got to be greater than 10, well, let's have a look at this, okay? So now, if I just redraw my distribution curve, and I've got a fresh one here, okay? There's my distribution curve. I want the probability that x is greater than 10. So in other words, any value which is greater than 10 is fair game, okay? So I know that the probability of ending up between 2 and 3 standard deviations above the mean is 2.35%. The probability of ending up more than 3 standard deviations above the mean is 0.15%. So if I add those 2 things together, what does that end up with? It's at 2.5%, okay? So that's going to basically be 2.35% plus 0.15%. That should give me a probability of 2.5%. So the probability of ending up with a value which is more than 10 for this particular distribution with a mean of 4 and a variance of 3 squared should basically be about 2.5% chance. Or another way of interpreting that, 2.5% of your data should lie more than 10 values, more than 10 above, okay? If I want to look at a between probability, okay, so let's have a look at this one. So the probability that I'm looking at a value between negative 2 and 7. Well, are you happy, first of all, in this case? Look, I've got a less than or equal to probability and a less than probability here. If this was a discrete random variable, I would have to treat those very carefully. So less than is very different to less than or equal to. But because it's continuous, okay, because it's continuous, I can have any value I like. Less than or equal to, they're the same thing. So let's bring up our probability distribution again. So let's have a look. Here it is, okay? And I'm looking for a value between negative 2 and 7. So between negative 2 and 7, I'm going to basically be looking at this region in here, okay, between negative 2 and 7. So that's 2 standard deviations below the mean and 1 standard deviation above the mean. So let's just look at the proportions. So let's look at the probabilities for each of these regions. So the probability of ending up between 2 and 1 standard deviation below the mean is 13.5%. The probability of ending up between 1 standard deviation below the mean and the mean is 34%. And finally, the probability of ending up between the mean and 1 standard deviation above the mean is also 34%. So all I need to do to work out this particular region here is simply just add these probabilities together. Okay, so 13.5% plus 34% plus 34%, and that should give me, let's see, well, it's 68 plus 13.5, that's going to give me 81.5%. Okay, so there's an 81.5% chance of ending up between negative 2 and 7. Or, another way of interpreting that, 81.5% of my data should lie between negative 2 and 7. Okay. Now, let's actually have a look at a slightly more wordy question. Okay, so let's have a look at question 3. So it is known that the heights of people in a college are normally distributed. Great, means we can use our normal distribution. Also, heights is a continuous random variable, so I know that we're good there, okay? Now, we know that they have an average height of 180 centimetres and a standard deviation of 5. So let's actually get this written down. Let's first of all start by defining our random variable. So I'm just going to say x, our random variable. Okay, it can be any letter you like, but I'm going to call it x. So x is going to represent the heights of people in my college. Okay, so the heights of people in my college. Okay, and I know, let's come back to the question, I know that this random variable, so the heights, are distributed normally, so I can say that x is distributed normally. Well, what's the two parameters? Well, I need the mean and I need the variance. So let's have a look. So the mean is going to be 180, that's told me there. So the average height is 180. Okay, so 180 goes there. And what is the variance? Well, I know the standard deviation is 5. That means the variance is going to be 25. I'm just going to write it as 5 squared though, just to make it a little bit clearer. Okay. So I need to first of all find the probability that a person chosen at random has a height less than 190. So let's have a look at that. So I want to find the probability that a person chosen at random, so x, is less than 190 centimetres. So what's that probability there? So first things first, I'm going to draw myself out a little normal distribution. So I'm just going to draw myself a little normal curve first of all, like so. I'm then going to put my outcome along the bottom, so that's my x, okay? And I'm going to look at my probability along this axis here. Now I just need to physically work out what the values along the bottom are going to be. So obviously the value in the middle, this value here, has got to be the mean. So in this case, the mean, let me make it a little bit straighter, the mean is going to be 180. So 180 has got to be here. Then I basically know I'm looking at 3 standard deviations each side of the mean. So I'm going to draw those values in, okay? And then I can actually physically say what those values are going to be. Remember, I'm looking at a unit of standard deviation for every single bar I go above or below the mean. So in this case, the standard deviation is going to be 5, okay? Because the variance is 5 squared, so the standard deviation is 5. So it means that when I go here, 1 standard deviation above the mean, I'm going to be looking at 180 plus 1 unit standard deviation. That's 180 plus 5. That's 185. And then another unit standard deviation will be adding another 5. So that's 190. That's 195. And if I go the other direction, so 1 unit standard deviation below the mean is going to be 175, and then keep going. So 170 and 165. So I'm literally looking at this as units of standard deviation. All right, fantastic. So I'm looking for the probability that x, my random variable, my height, is less than 190. So in other words, I'm looking for anything less than 190. So I'm looking for this particular region in there. Okay, so I just need to go and work out what's the probability of each of these regions. Well, I know the probability of ending up in a region down here is 0.15%. Probability of ending up in here is 2.35%. Probability of ending up in here is going to be 13.5%. Probability of ending up in here is going to be 34% rather. I've doubled it in my head. 34%. Probability of ending up in here is 34%. And the probability of ending up here is going to be 13.5%. So in other words, I just need to add together all of those probabilities together. So let's have a look. Oops. Let's have a look. So it's going to be 0.15% plus 2.35% plus 13.5% plus 34% plus another 34%, and then finally plus 13.5%. Okay, so if I add all these probabilities together, let's see what we get. So that should be 97.5%. Okay, so 97.5% of my values should be less than 190. Okay, now let's have a look at part B. So part B says, Joe knows that approximately 16% of people in the school are smaller than what he is. So they must be smaller than what he is. So it's less than, okay? What is Joe's height? So I'm basically looking at this curve. So let's have a look down here. I'm basically saying, well, okay, what is the probability that I have a height smaller than Joe? That's what I want to work out, and I don't know what Joe's height currently is. But I do know that probability should come out as 16%. That's literally what is given in the question, okay? So I know that I'm looking for a height which gives me a cumulative probability less than that probability is 16%. So whatever Joe's height is, I know that all of the heights less than that, 16% of that should be the probability. Okay. Notice that I'm talking about proportions in the questions. Well, I can still use probability to talk about it. So I know that approximately 16% of people are smaller. So that means the probability of finding somebody smaller is 16%. Okay. So let's bring up my curve again. So here's my curve, exactly the same as before, with my mean of 180 and my standard deviation of 5. And I'm basically looking for what value gives me a probability less than 16. It gives me a cumulative probability of 16%. So let's add it together. Let's just go for all the less than probabilities. So let's add this region together. So this region alone is 0.15%. I know that. Okay. So basically, let's just keep on adding probabilities together and see if we can get up to 16%. Okay. So that's 0.15%. Now let's look at the next region. Well, this region here is 2.35%. So that region there is 2.35%. Well, let's have a look. 2.35% plus 0.15%. Well, that's going to give us 2.5%. So we're not quite there yet. Let's add the next region in. So this region in here. Okay, so this region in here is going to be 13.5%. So 13.5%. Let's see what happens if we add on 13.5 in here. Well, 13.5 plus 2.35 plus 0.15, hey, great. That's going to give us our 16%, okay? So that's going to be 16% in total. So now we just know that we're basically looking at a probability, or we're looking at a region, which is less than 175. So that means that we can work out that Joe's height has got to be 175 because 16% of people have a height smaller than 175, okay? So therefore, Joe's height is going to be 175 centimeters. So hopefully that makes sense, okay? So just simply by looking at that, we know what the probability is. That means that we can work backwards to find out what Joe's height is. So okay, let's have a look at this question together. So it's a different question now. We've basically been given that x is a random variable that is normally distributed with a mean of 5 and a variance of 3 squared. So it's going back to the example that we looked at previously. Okay, but this time what we want to do is find the probability that x is less than 1. So let's actually draw this together. So we basically want to do this, use this distribution. We want to find the probability that x is less than 1. So actually let's just make a start. Let's just draw in our normal distribution as before. Let's draw a normal curve or a probability density function. The mean, the value down the middle, well that's 5. And then basically each standard deviation we move is going to be worth 3 units. Okay, so each unit of standard deviation is worth 3. So basically what we've got is if we move up, we've got 8, then 11, then 14. And if we move down, then we've effectively got 3, we've got 2, then we've got -1, and then we've got -4. Okay, so that's basically just moving 3 standard deviations above and below the mean. Now we want to find the probability that x is less than 1. Now, are you happy this is an issue? Okay, because this means we're no longer looking at a whole number of standard deviations above or below the mean, which means that we can no longer use this kind of idea of knowing what the region's probabilities are going to add up to. Because what we're basically looking at now is a probability less than 1. So here's 1 on our curve. Let me draw it in. Here's 1 on our curve. So there's 1. And we're looking for a probability less than 1. So the thing is, we don't know what number of standard deviations above or below the mean 1 is. So we need to work that out, okay? So because it's not a whole number of standard deviations, it's not going to be like 1 standard deviation or 2 standard deviations or 3 standard deviations below the mean. It's going to be like 1 point something standard deviations below the mean. We need to work out how many units of standard deviation 1 is, in this case, below the mean, okay? So let's actually do this, okay? So if we draw this in, here we go. We're looking for this particular value here. It's not a whole number of standard deviations below the mean. So we need to work out, well, how many standard deviations exactly is it below the mean? Okay. So what we need to do is we need to re-standardize this curve. Okay. This is something called the standard normal distribution. So at the moment we have a random variable which has a mean of 5 and a variance of 3 squared. So it's normally distributed with a mean of 5 and a variance of 3 squared. What I want to do is transform it to a distribution like this. So I want to transform it to a distribution which is still normally distributed, but the mean is 0 and the standard deviation is 1. Why do I want to do that, remember? Well, just remember the question which I want to answer is how many units of standard deviation is the mean from this? So at the moment I can't really do this, okay, using this curve. So what I want to do instead is center this distribution so that the mean is 0, so I don't have to worry about adding the mean or whatever. And I want to change these standard deviations not to be 2, -1, -4. I want to change them so it literally says this is 1 unit standard deviation, 2 units of standard deviation, 3 units of standard deviation. So what I need to do first of all is I need to shift it so that the mean isn't around 5, but it's around 0. That's really easy to do. All I need to do is take my outcomes and just shift them to the left by 5. So in other words, instead of it being centered around 5, let's center around 0. So just move the entire distribution to the left by 5. The way to do that is by taking all my random variables, so x, and take away my mean. Okay, so if I do that, they're now all centered around 0, which is fantastic. That's exactly what I want. However, I've still got an issue because if you have a look, I've still got 3, 6, 9, which I'm still dealing with 3 as my unit of standard deviation. I don't want that. I want that to read 1, 2, 3, and -1, -2, -3. That's really easy. All I need to do then is just stretch the distribution inwards so it's no longer 3, 6, 9. It's going to be 1, 2, 3. So I need to stretch it inwards by 3. Okay. Really easy way of stretching by 3 inwards is just dividing that distribution by 3, or dividing that distribution by whatever my units of standard deviation is. Okay. So if I stretch it inwards like so, we get a much nicer distribution, so it's now -1, -2, -3 on the left, 1, 2, 3 on the right, and 0 is the mean in the middle. Now you notice that by doing so, we've transformed that value, which was probability that x was less than or equal to 1, so the probability that we were after, is now telling us that 1 on this distribution, 1 on x, is actually just -1.33 units of standard deviation below the mean, okay? So literally all I've done is I've taken 1, I've taken away the mean, divided by the standard deviation, and I tell myself how many units of standard deviation above or below the mean that value is, okay? So in other words, I'm basically taking this distribution and transforming it to be this, okay? So if I actually transform this then, so let's have a look at our original question, let's just go through it together. I'm basically asking how many units of standard deviation is 1 below the mean? Well, I just simply follow my standardizing routine. So it's a standard normal distribution. In other words, I say how many units of standard deviation above or below the mean am I? I simply just follow this formula. So I take the 1, which is the probability that I'm after. So I'm after the 1, okay? I take away the mean, divide by the standard deviation, and I find that 1 ends up as -1.33 units of standard deviation below the mean, okay? Now, you might say, well, okay, that's fine. So I'm basically looking for a probability which is less than -1.33 units of standard deviation below the mean. How is that helpful though? Like, fine, I know that 1 lies 1.33 units of standard deviation below the mean, but why does that help? How is it going to actually help me calculate the probability? Well, fortunately, much like I just kind of gave you the probabilities of ending up in each region, there are something called standard normal tables, okay? So in other words, I need to look up in my tables what is the probability that I end up less than -1.33 units of standard deviation. And these are what the tables will look like, okay? So they look a bit confusing, but effectively all of these probabilities are the probability that you will end up at a value which is less than whatever value you're looking up. So these are all in terms of units of standard deviation, okay? So you can see the one on the left is all dealing with negative units of standard deviation, in other words, units of standard deviation below the mean, and the one on the right is dealing with units of standard deviation above the mean, okay? So let's actually have a look at this in a little bit more detail. I want to find the probability that I end up being less than -1.33 units of standard deviation below the mean. Now this is really important. The standard normal tables are always given as less than, never more than. They're always less than whatever unit of standard deviation you're looking up, okay? Which means that if you do want to look for a greater than probability, you're going to have to do 1 minus the less than probability. Because of course, the probabilities all have to add up to 1, okay? So if you do 1 minus, you'll end up with what you want, okay? So let's actually go here. I want to find what's the probability of ending up at a value which is less than -1.33 units of standard deviation. In other words, 1.33 units of standard deviation below the mean. That's the question, okay? So the way in which I do this, you notice that this kind of column here, and it's the same on both tables, just underneath the Z, that's basically your first two significant figures. So, or not your first two significant, your first two figures of the number of standard deviations you're looking up. So in this case, that'd be the 1.3 or the -1.3, okay? So I know that I'm going to be looking in this row because this row starts with -1.3 and I'm looking at the -1.3 from the units I'm looking up. And I know that this is all going to correspond to negative 1.3 something. So all these probabilities are less than negative 1.3 something. Then to work out how far I move across, I basically use the numbers along the top. Okay, so in this case, I want that sort of figure there to be a 3. So I'm going to move to this column here. Okay, so I'm looking at this column here. So where these two values intersect, that is the probability that z is less than negative 1.33. So in this case, these row and column intersect at 0.0918, which is going to correspond to 9.18%. So in other words, my original question, okay, which was what was the probability that x was less than 1? Well, I basically worked out 1 lies 1.33 units of standard deviation below the mean. And then from that, I was able to work out that probability using the standard normal tables should be 9.18%, okay? So let's actually have a look at these examples then. Let's have a look at these examples in a little bit more detail. So let's just go through question 1 together. And then I want you to go through question 3 as an applied learning task. So in other words, the weekly task for this week is question 3 on this particular slide. Okay, so have a go at this question here for a weekly task. But let's go through question 1 together, okay? Or at least as much of it as we physically can. So 1 is basically giving us a normal distribution. So x is distributed normally with a mean of 10 and a variance of 6 squared. And we are asked to find the probability that x is less than 0. So let's do that together. So let's find the probability that x is less than 0. Okay, so if I want to find this probability, first of all, let's just make a quick idea of where we're looking on our normal curve. So it does make sense to draw out our normal curve. So let's have a go. Okay, so the center value is 10, and then basically each unit of standard deviation. So this is going to be 16, this is going to be 22, and this is going to be, what's that going to be, 28. And then one standard deviation below, that's going to be 4, that's going to be negative 2, and that's going to be negative 8, okay? So that's basically what our normal curve will look at, looking at a whole number of units of standard deviation above or below the mean, okay? Now I'm looking for a probability less than 0. So 0, I know, is going to lie about there, okay? So I know that 0 is going to lie about there. So my question is, well, what is the probability of ending up at a value less than that? So in order to do this, it's not going to be a whole number of standard deviations, which means I can't use my kind of curve which I was using before. I'm going to have to standardize and use the tables, okay? So in order to do this, what I'm going to have to do is standardize. So remember the formula for standardizing is z equals, well, I'm going to take my value, which is 0. That's the value which I'm interested in finding out how many units of standard deviation above or below the mean I am. Take away my mean value, which is 10, and divide by my standard deviation, which in this case is 6. So okay, I have negative 10 divided by 6, which is going to be negative 10 divided by 6 is going to give me negative 5 over 3. Always give as a decimal those two decimal places, because that's how our tables work. So I'm looking for negative 1.67. Okay, so basically if I transform this, I'm no longer looking for the probability that x is less than 0. I'm basically saying, well, okay, what's the probability of finding a value which is less than negative 1.67 standard deviations below the mean? Okay, so negative 1.67. So in order to answer this, I'm going to come to my tables. Okay, I'm going to come to my tables. So okay, I'm looking for a probability which is less than negative 1.67. So remember the negative tables are the ones on the left. So let's zoom in on these and let's have a look at what we need. So negative 1.67 is the magic number. So negative 1.6 first of all. So I know that I'm going to be looking at this row because that's all the rows that start with negative 1.6, or all the units of standard deviation that start with negative 1.6. And I want negative 1.67. So I'm just going to move across and I know that I'm going to be looking in this particular row here. Okay, so I know then basically, let me just straighten that up so I can actually read it. So I know that basically I'm going to be looking at this probability here. So the 0.0475. So therefore the probability that I end up at a value which is less than 0, so x is less than 0, is going to be 0.0475 or approximately 4.75%. Okay, so 4.75% of my values. Okay, hopefully that makes sense. So let's have a look at this probability here. Let's have a look at the probability that we're looking at a value between 5 and 15. Well, okay, in this case, what I'm going to do is standardize each value separately because I need to work out how many units of standard deviation 5 is in relation to the mean and how many units of standard deviation 15 is in relation to the mean. So let's first of all do the 5. So we do z equals 5, take away our mean, which is 10, divide by a standard deviation, which is 6. So we get negative 5 over 6. So negative 5 divided 6. Is going to give us negative 0.83. Okay, so negative 0.83. That's how many unit standard deviations 5 is. Let's work out how many units of standard deviation 15 is. That's going to be z is equal to 15 minus 10, all divided by 6. Okay, this is nice and symmetric. That's just going to be 5 divided by 6, which is going to be 0.83. So this is a nice and symmetric one here. Okay. Now, always, always, always draw yourself a curve out. So I'm just going to draw my curve here. And I'll put 0 down the middle. And I'm basically going to be looking at 0.83 and negative 0.83. So this is negative 0.83. And 0.83 is going to be about there. And I'm basically be looking at values between there. So I'm looking for this region here. Okay. So I need to kind of think logically about how I can do this. Bearing in mind, my tables are cumulative. In other words, all the values up to that particular value. So what I'm going to do instead of looking at this kind of, looking at each separately, what I'm going to do first of all is I'm going to look at the region up until 0.83. So I'm going to look at the region up until 0.83 and work out what that is. And then I'm going to take away the region which is less than negative 0.83. So if I'm going to draw this out, I'm going to basically say, okay, let's first of all look up the probabilities up until 0.83. So let's find all of that region there. Now remember, I don't want all of that region there. I'm going to take away the region which I don't want, which is this region down here. So in other words, I'm going to take away these two regions. Okay, so I'm going to take the blue region, find that one first, take away the green region, and then I'll be left with the region in the middle, okay, which is the red region, which is what I want. Okay, so in other words, what I'm saying is that I'm trying to find, first of all, let's look on our tables for between 0.83 and negative 0.83. Okay, remember that less than or equal to doesn't matter about the difference. So the way which I'm going to calculate that is first of all find the blue region, which is the probability that z is less than or equal to 0.83. Let's write that properly. And then take away the blue region, which the green region, which is the region which I don't want. Okay, so I'm going to take away z being less than negative 0.83. So let's work out what these probabilities are. It says first of all look up the probability that I have a value less than 0.83. Okay, so this is the cumulative tables. Let's find 0.83 in my tables. There's 0.8, so I'm looking in that row. So this particular row. And I'm looking in the 0.3 column, so that particular column. Looking for the overlap. Okay, that's 0.7967. So I know that this probability all the way up there, let's zoom out a little bit, is 0.7967. Just found that, okay? Now let's look for the probability that it's less than negative 0.83. So let's zoom in at negative 0.83 then. So 0.83. And let's find the 0.3 column. So it'll be this one down here. Okay, so I'll look for the overlap. That is going to be 0.2033. Okay, 0.2033. So now all I need to do is subtract these two probabilities from each other. So let's have a look. Stick it in our calculator. We get 0.7967, subtract 0.2033. That gives us 0.5936, or that's going to be approximately 59%. So 59.36%. Okay. So in other words, 59.36% percent of values is going to lie between 5 and 15 of our original random variable. So, couple of things to remember here. You can absolutely, if it's a whole number of standard deviations, remember that curve and just remember what each region is corresponding to. But if it's not a whole number of standard deviations, you need to standardize and then use the tables, but bearing in mind that the tables are always less than. So sometimes you just need to play around and just figure out, well, okay, if I want a greater than probability, that's easy, just do 1 minus the greater than probability. If you want to do a between probability, then you need to be a little bit more creative. It's very visual. So always draw that curve out because it really, really helps. So please remember to do question 3 for homework for this week.